Hi, I'm Madison O'Neill, and I'm taking the Solid Mechanics Lab course right now. So today I will be giving a presentation over the shear force and bending moment in beams experiment that we did. So a brief outline of how this presentation is going to go. It will start with a statement of the objective, followed by a theory that will give you a little background information regarding the experiment that was done and why it's important. And then we'll go into the experimental setup, and then the procedure that we did use for this experiment, and then I will give you the data that was obtained during the experiment, followed by analyzing that data and the calculations that we did by hand, and then I will kind of discuss those results and then give you a short conclusion. So the purpose of this experiment was to become familiar with calculating shear force and bending moment, and then as well as going ahead and drawing those diagrams for the shear force diagram and the bending moment diagram. That was all for a distributed load in a cantilever beam. So what is shear force? Shear force is the sum of all the vertical forces acting along a beam. So the shear force diagram is an illustration of those forces, and it does illustrate the entire length of the beam, so you could go at any point along the beam and find the shear force acting on that point. Bending moment is the sum of all of the bending moments acting on that beam. Just like the shear force diagram, the bending moment diagram is an illustration of the entire beam, and you can find the bending moment at each point. So what is this used for? So calculating the bending moment diagram comes from the shear force diagram. So you calculate shear force, and then from there you can calculate the bending moment diagram, and you use that maximum bending moment diagram to find the maximum bending moment on that beam and input it into the flexure formula right here. So we have sigma equals MC over I. So what is sigma? Sigma is the maximum stress. So sigma equals the maximum bending moment M times C, which is the location, the centroid, the distance from the centroid to the outer surface of the beam, divided by I, where I is the moment of inertia. For this experiment, it was a rectangular beam, so the moment of inertia was calculated by the formula 1/12 BH cubed. And then also we have the Young's modulus formula. So we have Young's modulus E is equal to sigma over epsilon, where sigma is the stress and epsilon is the strain. So Young's modulus is used in a variety of applications and reasons. That's why this is important. If you have a certain stress that the beam is going to experience, you use Young's modulus to make sure that it can withstand that given load. So the experimental setup. So we use the SM1009 strain gauge trainer, and we use the bending system. It does also have a tension and torsion system, but we did not use those. We had sets of large masses and small masses, as well as a strain display. And then our additional equipment that we used was strain gauges, wiring, dummy gauges, and that's it. So this right here is the SM1000 strain gauge trainer. So along this point right here is our actual cantilever beam. Right here is the where we have 6 suspended masses along the cantilever beam, and I will go into detail how exactly this was set up whenever I move into the procedure, but just go ahead and note that these are evenly spaced and they do not start right at 0. They are offset from the left-hand side a certain extent. So the procedure. So first, a multimeter was used to make sure that the voltage source was 4.9 volts and that each of the strain gauges were 350 ohms. The bending system was connected as a full bridge mode, which is mode 4. And then a couple minutes were waited before zeroing the system. So this next step, it says that we measure the width and the thickness of the beam. However, we did not have any calipers within the lab, so what we did was we pulled up the specifications from the manufacturer's website and used those, assuming that the beam was those given dimensions. So you saw that the weights were offset from the left-hand side. So the reference point was actually set 100 millimeters or 10 centimeters from the left-hand side. And then from there, the first hanger was applied, the team grouped in centimeters from that reference point. So say it's group 3, the first hanger would be applied at 130 millimeters or 13 centimeters because it was the 10 centimeters plus 3 because that was the group number. So also, it was very important to make sure that none of the hangers exceeded 0.4 kilograms. So for our experiment, we used 0.3 kilograms on all of the hangers. So then next, the next hanger would be applied 3 centimeters from the previous one, and then this was repeated for however many hangers were needing to be used for that specific test. So we actually did it for 4 hangers, 5 hangers, and 6 hangers. As I mentioned before, each hanger had 0.3 kilograms of mass on it. So the strain value was recorded for each of these tests, and then hand calculations were performed to find the theoretical and actual values of stress. So by hand, each of the beams with the distributed load was drawn, and then the reaction forces were determined, and then the shear force diagram, bending moment diagram, all those were drawn for each of the 3 configurations. And then lastly, we did use a computer calculator to also find the shear force diagram, bending moment diagram, and reaction forces for each of the 3 loads to compare with our values. So this right here is our experimental data. So what I want to point out is the moment of inertia was calculated to be 208.333 millimeters to the fourth. So that was the formula that I mentioned earlier, 112 BH cubed. And then we were also given a Young's modulus of 200 gigapascals for this beam. So that was a given value. So we have each of our 3 tests, the 4, 5, and 6 hangers. As I mentioned before, 0.03 kilograms on each hanger, the total load applied, and then the total force once we converted it into newtons by multiplying by gravity, and then the displayed tensile strain that we have here. So for the first load, it was 21 microstrain, the second one 28 microstrain, and the third one 36 microstrain. So you can see that it does increase as the number of hangers increases. So the analysis of data and calculations. Right here I have our calculations for the loading with 4 hangers. So as you can see up here, this is the beam drawn, and then the 4 hangers, and then the reaction forces for the y direction and the reaction moment. So the reaction force in the y direction was 1.1772 newtons, and then the reaction moment was 241.326 Newton millimeters. So from this, it was used to draw the shear force diagram. So since we had a reaction force in the y direction acting upwards, the shear force diagram starts at 1.772 in the positive direction. That is, there's no more force applied until we reach the distributed load, so that remains level. And then once we find the distributed load, it does increase or decrease linearly back to the 0 point. And then from there, we calculated the bending moment diagram by taking the area under the shear force diagram, and that's how we get our maximum bending moment and how much it decreases along the beam. The same thing was done for the loading with 5 hangers. As you can see, the reaction forces did increase, so we have 1.4712 newtons in the y direction now, whereas before it was 1.1772. And then the reaction moment also increased as well with 323.664 Newton millimeters. The diagrams were drawn the same way. You can see our maximum bending moment is at the all the way at the left-hand side as well still, and that was 323. So the loading with 6 hangers, same as the previous 2. I do want to note that it did continue to increase. Now we're at 1.7658 newtons for the reaction force in the y direction, and our maximum bending moment was 414.893 Newton millimeters. So analyzing this data. So for each of the tests, we, like I said, we had a displayed tensile strain, and then we also calculated the tensile strain. So this is the two that are being compared here in the percent error. So the displayed values here and the calculated tensile strain here. This had a significant percent error of about 45%. This does mean that something was indeed wrong within the experiment. I will talk about the reasoning behind this later, but go ahead and just see we have 21 and 14.48. I mean, those are very big differences between those. And how we calculated tensile strain with the hand calculations, we took the bending moment and the calculated tensile stress, we got that from flexure formula. And then we used that within the Young's modulus formula, E equals sigma over epsilon, rearrange that to solve for the strain. This is a plot that shows the difference between the two. They did both increase linearly, even though there was that percent difference, but it is definitely clear that they were not the same values. So these are the different data points that were found between the calculated values and the computer values. So very good results here. There was a percent error of virtually nothing on either side. Very, very small, 0.00024% for the loading with 6 hangers in the shear force. That was likely due to rounding. Same thing for the maximum bending moment, 0.01699%. Very, very small, again, likely due to rounding for the bending moment. As you can see here, there's no clear difference between the calculated values and the computer values between the shear force and bending moment. So what does this mean? As we saw, the distributed load increased, which also resulted in the tensile strain increasing. So those are directly related with one another. And then it is important to say that after the load was removed, when changing from 4 hangers to 5 hangers to 6 hangers, the tensile strain reading did return to 0, which indicates that no permanent deformation was done through the loading. So the hand calculations did align almost identically with the computer calculations from that software, which really verifies that both of those are two good methods to use. However, the percent difference between the experimental values and the calculated values was 45%. It's very, very high. A likely cause of this could have been our assumption of the beam dimensions. Since we did not have calipers, maybe there was a tolerance that we didn't know and the beam was not the dimensions it was supposed to be, or the specifications were out of date. Something like that could have really altered our results. Or there was something wrong within the experiment that we didn't know. The equipment was already set up prior to us arriving. There could have been something within that was incorrect. I know that there have been issues with this piece of equipment before, so that could be a reasoning as well. And then the references used were the shear force and bending moment in beams lab guide, and the bending testing and bending deformation of a cantilevered beam lab guide as well, and then our theory of shear force and bending moment lecture. And then lastly, this is the website that we used to calculate the bending moment and shear force software to get those calculations. Thank you.